A humble child's climbing structure here holds a host of mathematical intricacies. And I should take a look at the structure and notice that there are certain patterns that recur. It's made up of these metal curved beams, and the metal curved beams are joined by red spherical hubs. And if you look at each hub, you will see that 5 of the beams meet at each hub, and moreover, the shape made by hubs that are nearest each other is always a triangle. So it's a triangular shape, and so that's this structure here called an icosahedron. I've made them all different colors so you can easily see all the different triangles and how there's a 5 at every vertex. And people have been wondering how to put two-dimensional shapes together to form three-dimensional shapes literally for millennia. And so these shapes are named after a guy called Plato, you may have heard of him, who said, if we want to have all the sides be identical and all the corners be the same, what are the possibilities? Here's one. It's called a regular dodecahedron because there's 12 identical pentagons with 3 meeting every vertex. Turns out there's only 5 of these shapes. I think there's another one that you might be able to see if you kind of look around the city. Maybe not right by us, but kind of visible from here. Anybody see another platonic solid in the skyline of the city visible from this point? Probably a cube, right? Buildings do tend to be more rectilinear. Anybody see a cubical building? Yeah, the Perot Science Center behind me is in the shape of a cube, with one big kind of noticeable interruption or addition to the cube. What do you see? Yeah, a big black slash on the side, and that goes back to what we were talking about accessing buildings. It's the human needs to get into the building. In that case, that's the escalators that create that big addition to the cube. Okay, I do want to say one other thing, because there's another mathematical gem, almost literally hidden inside. At the very center of this, you see there's a network of ropes. And those network of ropes, it's this shape right here. I'll kind of push it. Yeah, you can see it started to lose some facets and so on. But it's this shape right here. What do we call this? Soccer ball. Yeah, you can call it a soccer ball. It's where we often see it. A chemist might call this a Buckyball because it's the structure of the molecule formed from 60 carbons called Buckminster fullerene. But a mathematician might call it a truncated icosahedron, which kind of brings out the relationship between the inner and outer shapes in that structure. And this is interesting, and remember I promised to explain why this is maybe the most mathematical object in the whole park. It's because, well, what is the most symmetric three-dimensional object possible? Yeah, a sphere. It makes us very happy because you can rotate the sphere by any amount and it kind of looks the same, right? Any possible rotation leaves the sphere the same, and that's why we say it's the most symmetric, because one of those rotations that leaves it the same, we call that a symmetry of the object. So how many symmetries does this object have? Well, you see, if I hold it like this, I've got this vertex on top, and the pentagon is pointing straight toward you. Now, Barb, I'd like you to pick any other vertex of this structure. Just point to one of the corners. Come on over. That one right there, okay. Well, I can move that one on top, and then I can point the pentagon directly at you, and ignoring the slight imperfections in this one, it's now in exactly the same shape it was before. So there's one transformation, one symmetry for every vertex of the structure. That gives us 60 different symmetries, because there are 60 vertices on this structure. Plus, we can always take a mirror and reflect it in a mirror, and that doubles the number of symmetries. For every one of those, we could then add a mirror reflection. So there are 120 different symmetries of this object, and it turns out, mathematically, that is the largest number of possible symmetries for any three-dimensional object. I don't care how complicated or simple a structure you make, if it's not a sphere, the most it can have is 120 symmetries, just like the truncated icosahedron at the center of this structure. So that, I would say, from that point of view, makes this the most mathematical object in the park.